Hi everyone, this is Mrs. Jennings with our second screencast for Honors Anatomy and Physiology. This screencast, the topic is homeostasis, and by the end of this screencast you should be able to explain what homeostasis is and its importance, be able to explain the control mechanisms and the components for maintaining homeostasis, be able to distinguish between positive, negative, and feed-forward feedback loops, and be able to summarize thermal regulation and the regulation of blood sugar levels in our body. So let's begin. You'll see here on the screen a gymnast performing her routine on the balance beam, and you'll notice that she is keeping a very good balance. Otherwise, she wouldn't be still on the beam. So, homeostasis, the reason why that's there is it's a good analogy for what homeostasis is. Homeostasis is the ability of the body to maintain a balance or an equilibrium or a set point or a steady state of things that are going on in your body. For instance, your body temperature has to be 98.6, so it has to maintain that 98.6. If you were to get hot, body temperature goes up, you got to have a way to get it back down to where it belongs. And this could be true too of your blood sugar levels in your body, your calcium levels in your body, your potassium levels, your water levels. So there are many different parts within your body that have to be maintained at an equilibrium, and that's what homeostasis is. And so on this slide, you'll see two examples of homeostasis, and there are many more, but I did put thermal regulation and blood sugar level regulation up here because I want you to be able to summarize how those mechanisms work, and I will go over that in a couple of slides. Examples, thermal regulation being body temperature control. You'll see as this runner begins to run, his body temperature is going to increase beyond 98.6, so there's got to be a mechanism in order to cool that body temperature off. Blood sugar level regulation. When we eat, we get sugar from the food, we get high levels of sugar floating through our blood, and our cells of our tissues need that sugar. So we have to have a mechanism to deliver that sugar into the tissues and not keep it in the blood where our blood sugar levels will rise. Two body systems that are very important in homeostasis is the nervous system sending signals and the endocrine system, which will send hormones to help cause some of these responses to maintain homeostasis. If we cannot maintain homeostasis, then we could develop a disease state or even possibly death if the homeostatic control was far enough out of its set point. So homeostatic control mechanisms is what I'm going to talk about next, and these are just processes for maintaining homeostasis or restoring homeostasis if it gets out of whack. And within this homeostatic control, you're always going to have three basic components of the feedback loop. And these three basic components are going to be the sensor, which senses the change from the set point. So we've got a set point. It could be a set point temperature, set point blood sugar, whatever it is. Sensor senses it. When the sensor senses it, the sensor is going to then send a signal to the integrator. Integrator usually is the brain. The brain will then make a decision what to do, and then it will send a signal to the effector, and the effector will be what actually makes the change. So as we send from the sensor to the integrator, this is called the afferent pathway, afferent with an A, and as we go from the control center to making a response, it's called the efferent, efferent with an E. Okay, so we got the afferent starting with an A and the efferent with an E, afferent being sensor pathway and efferent being the pathway to make a response. Now, of the feedback loops, there are going to be three. you're going to have a negative feedback loop. This negative feedback loop is called inhibitory because it's going to inhibit the change from the set point. Whatever the set point was, the negative feedback loop is going to change it back to the way it was. So it's going to inhibit or oppose that change. Our second type of feedback loop is a positive feedback loop, and it's going to be a stimulatory. It's going to stimulate a change. So we deviate from the set point and we continue deviating from the set point. That's what a positive does. And then our other type of feedback loop in our body is the feed forward. A feed forward anticipates there's going to be a set point change, and so it starts to respond before there's a set point change. So it is anticipatory. It anticipates the change and does something before the change actually happens. So these are our three feedback loops using these three basic components, all of which keeps are used for processes to keep us in homeostasis. And the negative feedback loop is the most common in our body. Now I put a thermometer up here because it's a really good analogy of how homeostasis works, and especially how the negative feedback system works. On this thermostat, it is set at 70 degrees. The room temperature here is also 70 degrees, but if this room temperature were to rise to 74 degrees, there's going to be a sensor inside this thermostat that will sense it, send a signal to the integrator. The integrator will then tell the air condition and fan to kick on, and the air condition and fan will kick on and oppose this change. And it will kick on until we get the temperature back to where we have it programmed. And so that would be an analogy of what goes on in our body for homeostasis and these feedback loops. And this would actually be a negative one because you're inhibiting the change. Okay, so let's look at thermal regulation specifically in our body. Okay, we start out with a set point. Our set point is 98.6 in our body. And if we deviate from that, we have got to fix the problem. So in this picture, we have the temperature dropping, we have range, this hiker's getting wet, so her set point is changing. There's a variable, and her temperature is decreasing. And the skin sensors will pick that up. They will send a signal to the integrator, the brain. The brain, and the hypothalamus is the exact place in the brain that senses that. The brain will then send a signal to the muscles, which would be the effector. So we have sensor, integrator, effector, and the effector would actually cause the muscles would be the muscles shivering. Shivering is contracting of the muscles produces heat, body temperature comes back up to normal. Okay. Now if the opposite were to happen and this hiker was overheating, the same sensor would sense it, send it to the same integrator, but the response this time would be different. The response would be dilating blood vessels in the skin to release the heat and to sweat to have heat be removed with water. So you have followed this process here for homeostasis, and that is a negative feedback system. And here is another negative feedback system. And this one has to do with blood sugar levels. Now we need blood sugar in our body, or we need sugar in our body, and it enters our body from our food into our blood, and then our blood delivers it to our tissues. So if the sugar in our blood becomes low, as you can see here, if it becomes low, our body has cells all over it that will sense it, and those cells will send signal to the pancreas. So in this case, the pancreas is going to be the integrator. Okay, the pancreas alpha cells will release a hormone, and the hormone is called glucagon. Now, glucagon is going to cause the sugar that has been stored in the liver as in the form of glycogen to be released. So glucagon is going to be the effector, the pancreas was the integrator, and the cells all over the body were the sensors. And this change of glucagon causing glycogen to become glucose is going to put sugar back into the cells. So we've posed the low blood sugar and put sugar in the cells. Now what if we have high blood sugar? So we've just eaten a really high filled sugar meal, and there's a lot of sugar floating around in our blood. Okay, our cells are going to sense it. Our pancreas is going to integrate what to do, and the beta cells of the pancreas in an area called the islet of Langerhans is within a small area of the pancreas, is actually going to produce insulin. Now insulin is a hormone just like glucagon is a hormone, but insulin does the opposite as glucagon. Insulin will cause all this extra glucose to be stored into fat cells in the form of glycogen in the liver, and it will also be the vehicle that drives sugar into the tissues in order for it to be used. So insulin is the effector. It's going to cause that sugar level to, the sugar to be removed from the blood and put somewhere else. And so then you're getting back to your set point. Okay. Now there are two other feedback loops that I mentioned, positive and feed forward, although most of our body has a negative feedback system. But I do want you to know that a positive feedback loop, an example would be childbirth. Now what happens in childbirth is that by 9 months the uterine wall and the cervix start stretching. And that's a change from the set point. So there are stretch receptors in that muscle lining that uterine wall. Those stretch receptors will then send a signal to the brain. The brain will integrate it, and the brain will send a signal to the muscles by way of a hormone, and the hormone is called oxytocin. Oxytocin is a hormone in the body that will actually cause the muscle of the uterus to forcibly contract. So this forcible contraction is obviously important in order to actually cause childbirth to occur, for the baby to be pushed out of the uterus. Now, when this oxytocin is released, instead of relaxing, it actually stimulates more oxytocin. So we go around in a circle with oxytocin causes contraction, causes more oxytocin, causes more contraction, causes more oxytocin, causes more contraction. So you're actually stimulating instead of stopping what the variable change was. So this is considered a positive feedback loop. Our white blood cells responding to infection works the same way. More white blood cells are made because more white blood cells, so you're actually stimulating. And then the feed-forward system is anticipatory. So you smell food, that wonderful aroma. It causes your salivary glands to release saliva in your mouth. And saliva is part of the process of digesting food, which then also causes acid to be increased in your stomach so it can digest food, but you haven't put one bite of food in your mouth or digestive system yet. So it's anticipating it's going to happen, and it's already making changes that are going to effect that change, but it did it before it happened. So feed-forward feedback loop is another type of feedback loop. So you had positive feedback loops, negative feedback loops, feed-forward feedback loops. You had the three mechanisms within this homeostatic feedback loop system called the sensor, the integrator, and the effector. And then you also had a definition to homeostasis, and you had thermoregulation and blood sugar regulation as examples. You are now ready to take the second whisk on homeostasis. And I'd like to also, before I conclude, give a shout out to the cats for tomorrow night. Good luck, and I will see you guys tomorrow in class.